Hello students, welcome to Pi Academy, the place for mathematics and science. Dear students, in the last class we were discussing the chapter magnetic effects of electric current, right? Now let's go for continuing this, and remember this is the second period of this chapter. In the very first period we got the basic information about this chapter, right? Now let us go for recalling these point by point. The very first point, it is definition of magnet. How do you define magnet? A substance which attracts iron and iron-like substances and comes to rest in north-south direction when it is suspended freely is called a magnet, right? And we also know that magnet is available as a ore. So then could you tell what is the ore of magnet? Yes, you are right. It is magnetite. Once I repeat, the ore of magnet is magnetite. Then magnets can be classified into two types. One is natural magnet and second one is artificial magnet, right? Then give an example for natural magnet. This is lodestone, also called leading stone, right? Next, artificial magnets, we can give the examples and name can be given based on their shapes, like bar magnet, horseshoe magnet, magnetic needle, ball-ended magnet, then circular magnet, ring magnet, spherical magnet, like this. So many examples can be given for artificial magnet. Then after this, we recall important properties of magnet. What are those? The first point, general property it is. Magnet, it can attract iron and iron-like substances, right? And second point, it comes to rest in north-south direction when it is suspended freely. And third point, like poles of two magnets repel each other and unlike poles attract each other. Third point, fourth point, every magnet has two poles, one is north and second one is south. Fifth point, poles of a magnet cannot be separated, right? And sixth point is, a magnet loses its magnetic property when it is heated strongly or when it is beaten with the hammer or when it is dropped from the great height. These are the important properties of magnet. Then we also learned that law of magnetic pole. What it is? Just we told that in one of the properties, that is, like poles of two magnets repel each other and unlike poles attract each other. See that here, north and north, these will repel each other. South, that is south pole of one magnet is brought nearby the south pole of the another magnet. They repel each other. Suppose north pole of one magnet is brought nearby the south pole of another magnet. They attract each other. Even south pole is brought nearby north pole, again they attract each other. And this is what we say, law of magnetic poles. It is also called magnetic effects. Okay, then after that we have come across another important term, that is magnetic field. Magnetic field, very important term it is. So I am just putting star mark. What is magnetic field? Yes, it is the region around a magnet where the magnetic force is present and the magnetic effect is felt, right? It is denoted by the symbol capital B over that arrow mark. Once I repeat the definition, as it is very important, the region around a magnet where the magnetic force is present and the magnetic effect is felt is called magnetic field. And magnetic field can be measured with a unit called, yes, it is Tesla or Weber per meter square. Whatever the magnetic field is present around the magnet, is it possible to see? No, they are invisible. Hence, they are represented with set of lines. What do you call these? These are called magnetic field lines or magnetic lines of force. Here I'll write. It is magnetic lines of force. Lines of force. Yes. Then, and this magnetic lines of force has some of the important characteristics. Just recall them. And before that, and we know that pattern of magnetic lines of force is different for different magnet, but we had shown the pattern of lines around bar magnet, right? Just observe it. These are the lines of force, and here also I am drawing, and this was also asked in the examination many times. You must practice this. Here also, just keep observing how the lines, nothing but field lines, and the characteristics are First one, observe all these magnetic lines of force. Do they intersect each other at any point? No. You can notice that the lines of force do not intersect. Second characteristic, conventionally we take the lines of force emerge from the pole north and end at south. Clear? And another one. And these magnetic lines of force very strong enough such that they can pass through the materials like glass, paper, skin, bone and all. Next, one more point. You can notice that lines of force are maximum at the poles than at the middle. Why? Because magnetic field strength is maximum at the poles. Next, one more point. As the lines of force away from the source, nothing but magnet, then the field strength decreases. Here, when you name these lines of force as A, B, C, just for our reference, which one is more strong? Obviously, it is C, because it is very close to the source, that is magnet. Clear? So, after getting this information, then we recall a part of this chapter that is called electric current, which we have already discussed in the chapter electricity. How do you define electric current? Yes, it is the rate of flow of electric charges is called an electric current, and electric current is denoted by the symbol, it is I, and the formula, it is I is equal to Q by T, where I is electric current, Q is quantity of charge and T is time. Current can also be written as NE by T, because quantity of charge is nothing but N into E. Next, what is its SI unit? Electric current can be measured with a unit called, it is ampere. Ampere, and the actual unit is, it is coulomb per second. Right? Then after that, we learned one of the important statement which give the relationship between electric current and magnetic field. Who has shown this? It was shown by Hans Christian Oersted through his experiment. It is familiarly known as Oersted experiment. Let us go for that experiment in the later. Before that, just I'll tell you the statement which gives the relationship between these two, electric current and magnetic field. Imagine that there is a circuit, and assume that it is a wire that is used in the circuit. When the electric current flows in that, then magnetic field is developed around this conductor, and we call this effect as the name of our chapter, that is magnetic effect of electric current. Got it? Here, once we shall recall the definition of magnetic effect of electric current. Very important. When an electric current flows through the conductor, the magnetic field is developed around the conductor. This is known as magnetic effect of electric current, and it was discovered by Hans Christian Oersted. Hence, he is called father of magnetic effect of electric current. In this chapter, we are going to learn about magnetic effects of electric current. So, now before going to that, just I told you the relationship between magnetic field and electric current was discovered by Hans Christian Oersted, and the experiment is known as Oersted experiment. Now let me go for explaining Oersted experiment. Yes. Now let me explain Oersted's experiment. What is this experiment? What is the aim of the experiment? His intention is to show electric current can produce magnetic field. Hence, here I write aim of the experiment as to show electric current produces magnetic field. Here it is electric current. That's why he has made a simple arrangement by taking wire, switch, battery, then magnetic compass. Look here. Here, the free ends of the wire are connected to positive and negative terminals of a battery along with the switch. Then he will go for placing the magnetic needle or magnetic compass just below the wire. Got it? And observe here. This is facing towards the north, and this is the north pole of the magnetic needle. Here, when you switch on, the current start flowing from positive terminal to negative terminal of the battery. Then here, the north pole of the magnetic needle deflects towards east, right? Clear? And when you observe from here, see the current is flowing downward. So the needle is deflecting towards left or right? It is towards left. You should imagine in this direction. So I'm standing in the same direction. See the current is flowing from here, top to bottom. So then the needle gets deflected towards the left side. Similarly, here you can notice that suppose when the terminals are interchanged, look here negative and here positive, then the current obviously flows from positive terminal to negative terminal. This time it deflects towards west. North pole of the needle deflects towards left side. That means here the current is flowing in the upward direction. I am standing in the same way. See that? Current is flowing in the upward direction and needle deflects towards left. Why it gets deflected? If the needle present in the magnetic compass get deflected in presence of magnetic field only. Where is that magnetic field? It is due to electric current. See that? As electric current flows through entire circuit, the field is developed around it, and this magnetic compass is under the influence of the magnetic field which is developed around the wire. That is why it gets deflected. You can just imagine that when two magnets are brought each other, they may attract or repel, depends on the pole. Here also, as the magnetic compass is under the influence of the magnetic field produced by the current, then it gets deflected. And the direction of current can be known. For this purpose, one scientist has made a rule. He is Ampere, and the rule is known as Ampere's swimming rule. What it is? Ampere's swimming rule. What is that? See that. According to that, you have to imagine a man swimming such that the current is, a man is swimming in the direction of flow of current. That means current enters from his foot and leaves to the head. Then you have to assume that his head indicates north pole of the magnetic needle. And when he is swimming, every time he will go for swinging his hands, right? In the left hand indicates the direction of deflection. Clear? See, the current is flowing my left to right, then magnetic needle get deflected towards my left. Here also you can come to know that the direction of flow of current. Observe it. Here this is the direction of flow of current downward, and this is positive terminal and is negative terminal. Current flows from positive terminal to negative terminal. What about the deflection? Towards left or right? It is towards left. Clear? Similarly, in this case, see the current is flowing in the upward direction. This is positive terminal and this is negative terminal. And again, needle deflects towards left. Clear? So now let me go for writing the procedure of this experiment. Not only that, even I'll write statement of Ampere's swimming rule. And before that, once I make you to recall Ampere's swimming rule, it states that imagine a man swimming in the direction of flow of current such that the current enters from his foot and leaves from his head. Then head facing towards the north pole of the magnetic needle, and his left hand indicates the direction of deflection of the magnetic needle. Clear? Actually, this statement is not there in the textbook. Only for the sake of understanding the direction of the deflection of the needle, so we can learn that. Yes. Now you will go for writing from here. Oersted experiment. Then aim of the experiment. Then draw these two figures. Now I will go for writing the procedure. Observe. Here I have written the procedure. You will have to copy this. Hope that you have drawn these two figures, and the explanation has been written here. First, we have taken the plug key, battery and the wire. They are connected in series. Then after that, we are going to place the magnetic compass just below the straight wire. Then close the circuit. Then current flows along the wire. Here, see that from north to south. When the current flows from north to south, then the north pole of the magnetic needle deflects towards east. Next, if the current flows in the upward direction, nothing but south to north, then the north pole of the needle in the compass deflects towards west. Anyhow, see that when you stand like this, current is flowing from my head to feet, then my left hand indicates the direction of deflection of the needle. Then when the current flows from my feet to head, then the direction of deflection of the magnetic needle, again it will be on the left hand side. So that only has been written here. And here Ampere's swimming rule is there to know the direction of deflection of the needle. See that. It states that imagine a man swimming along the wire. If the current enters his feet, this is his feet, and leaves from his head, then that means the direction of current is from feet to head. Then his left hand indicates the direction of deflection of north pole of the magnetic needle. See that? It's very simple to understand. Yes, please go for copying this neatly. Dear students, just we have come to know that when the electric current flows through the conductor, magnetic field is developed around it. And we also know the magnetic field which is developed is not visible. Hence it is represented with a set of lines, and these lines are called magnetic lines of force. Even we have already learnt in the very first period of this chapter that the lines of force, pattern of lines of force is different for different magnets. Because the shape of the magnets will be differ from one to one. Similarly, here also we can go for study the pattern of lines of force around the conductor carrying current. But in how many ways the conductor can be conductor carrying current can be used. It is in three ways. Do you know how? One is, see that, assume that this is the conductor. How it is? It is straight. When the current flows through this, magnetic field is developed. But how will be the pattern? Let us come to know that later. Similarly, now it is the conductor. Now you tell that. Yes, it is circular conductor carrying current. In this also, magnetic field is developed. Let us come to know the pattern of lines of force afterwards. Not only this, then how it is. Conductor is just like a spiral which is called solenoid. So here also we can study the pattern of lines of force around conductor carrying current. So conductor can be used in three ways. What are those? One is a straight conductor, second one is circular conductor, third one is spiral or the solenoid. Okay, yes, let us go for studying. Just I told you, the conductor carrying current can be used in three different ways. One is as a straight conductor, second one is a circular conductor, and third one is solenoid. Here, let us learn one by one in detail. See, the first one, to learn about pattern of lines of force, nothing but pattern of magnetic field lines around a straight conductor carrying current. Here, then there is a simple activity. Let me show you that. Just keep observing them. And the diagram is also very simple. Here, I am going to take a straight conductor. Then, here is a cardboard, a square shaped cardboard. A hole is made and wire is inserted through this hole such that the wire should be perpendicular to the surface of the cardboard, like this. See that scale is perpendicular to my hand, that is my palm, in this way. Then let us connect these free ends to the terminals of a battery along with the switch. Look here, just keep observing the way I am going to draw. Of course, I will give you time for drawing. Observe here, this space I use it for battery. Longer line represent positive terminal, shorter one negative terminal, and battery is a combination of two or more cells. This is positive and this negative, and this is the switch, battery switch. If you want to vary the current, obviously you have to vary the resistance. Hence, for this purpose, you can go for using the variable resistance, nothing but a rheostat. Got it? Yes. Then, how we can study about the pattern of lines of force around the straight conductor carrying current? Let me go for explaining this. Very simple. The first point. Take a square cardboard and make a pinhole at the middle. Take a long copper wire and insert one end of it into the hole such that the wire should be perpendicular to the surface of the cardboard. Connect the free ends of the wire to the terminals of a battery along with the switch and variable resistance, nothing but rheostat. Then after that, next take iron filings and spread them evenly on the cardboard like this. See that? Iron filings are spread evenly. Next, after that, what should be done? Yes, let us close the circuit. What happens? The current starts flowing from positive terminal to negative terminal. See, just keep observing the direction which I have been showing. Positive terminal to negative terminal. Dear students, just we have learned that when the current flows through the conductor, then magnetic field is developed around it. Now see that here magnetic field is developed around this wire, and you just take only this part. As the magnetic field is developed, the iron filings, they are under the influence of magnetic field which is developed around the wire. What happens? when iron filings are there nearby the magnet, they start moving towards the magnet. Here also, the iron filings will gain the tendency to move towards the wire because this wire acts as a magnet. Now what you should do is, you just go for tapping this cardboard once or twice. Then immediately the iron filings will arrange themselves around the wire in this way. Just keep observing. So these are the iron filings. No doubt they will arrange in this way only. Now could you tell, this arrangement of iron filings will indicate the pattern of lines of force. What is the pattern of lines of force? Yes, it is. Do you say that just circles? No. Why? You just keep observing all these circles. They are having the same center but different radii. Yes, they are called concentric circles. And from this activity, we can conclude that the pattern of lines of force around a straight conductor carrying current, it will be concentric circles. Clear? Okay, here if the current is flowing in this direction, here lines of force are formed, and these will be concentric circle. Second circle, third one, and then fourth one in this way. Clear? This is the pattern. Pattern is concentric circle. Dear students, even we also know that these lines of force are having the direction. Now could you identify what is the direction of lines of force? If it is circle, we have only two possibilities. See that? What is this direction in case of circle? It is clockwise. If it is in this way, by left to left, left to left, like this, it is anti-clockwise. Then here, what is the direction of lines of force? To understand this, one more scientist, that is James Clerk Maxwell, he has given the law, and that law is known as Maxwell's right hand grip rule, Maxwell's right hand thumb rule also. Then from that rule, we can come to know the direction of lines of force. Then what is the statement? Look here. According to Maxwell, imagine a man holding a straight conductor carrying current. Straight conductor carrying current. And his thumb point, see this is thumb. The thumb point indicates the direction of flow of current. That means current is flowing from here to here. The direction of flow of current. Then these fingers, encircled fingers, indicate the direction of lines of force. The direction of magnetic lines of force. Clear? Once I make the statement, listen carefully. Very simple statement. Right hand thumb rule or Maxwell's right hand grip rule. Both are same one. Imagine a man holding a straight conductor carrying current in his right hand. His thumb point indicates the direction of flow of current, and the encircled fingers indicate the direction of field lines. Here the current is flowing upward direction or downward direction. Yes, you are right. It is flowing in upward direction. Encircled fingers, whether they are in anti-clockwise or clockwise. See that? This is anti-clockwise or clockwise? It is anti-clockwise. Right? If the current is flowing in the downward direction, see that? Here, the thumb point, it is downward. The current is flowing downward direction. What about encircled fingers, which indicate the lines of force? The direction will be clockwise. Clear? See that? It is clockwise in this way. So here, current is flowing downward or upward? Here, downward. So that, what will be the direction of lines of force? It is clockwise. See that? Clockwise. You can show the direction. Clear? Very simple. Assume that this is the point which indicates the current is flowing in this direction. See, current is flowing in the upward direction. If the current flows in the upward direction, then Clockwise or anti-clockwise? It is anti-clockwise. See that? Like this. And now current, it is flowing downward. Now this is clockwise. When the current flows downward, direction of lines of force is clockwise. If the current flows in the upward direction, the direction of lines of force will be in the anti-clockwise direction. Clear? Yes. Now, okay. And one more point. Here, whatever the magnetic field is developed around the conductor, maybe here, here, here or here, it has some strength, right? But my question is, whether the strength of the magnetic field which is developed around the conductor carrying current depends on any factors? Certainly, it depends on some factors. Then what are these factors? Factors on which magnetic field is developed or strength of magnetic field in case of straight conductor carrying current depends. One is, the very first one is the amount of current that flows. See that here, suppose this is 6-volt battery. It shows some amount of magnetic field, assume that 10 Tesla. If it increases 8 volt, 10 volt, whether field strength increases or decreases? Certainly increases. Why? As the amount of current flows in the entire circuit increases, the magnetic field which is developed around the conductor also increases. As a result of it, field strength also increases. First one is, it depends on amount of current. How? Magnetic field is directly proportional to current. As current increases, field strength increases. As current decreases, field strength decreases. So for that purpose only here we have used a rheostat. You may increase the current or decrease the current, and based on that you can check that. You can come to know. Next, another point. It is, observe here, just whatever the wire is taken, it is just made one rectangle only. You can also go for joining like this. See that wire is taken, it is made one rectangular shape, then another one, third one, fourth one, fifth one. At last you may connect this to terminals of a battery. Now whatever the field strength is there in this case, as the number of turnings increases, what happens? The field strength also increases. Why? Observe it. Here is one wire, then it has some field strength. In the same one, and another wire has passed. Here some strength, and this is some strength. As the number of turnings increases, the field strength will add together. Hence, it also increases. Hence, we can write B is directly proportional to number of turnings. As number of turnings increases, field strength increases. Number of turns decreases, field strength also decreases. Clear? Next. Okay, now let me go for writing the procedure, and please go for copying from here. From there to here, then after that you copy this also. Got it? Now after copying, you have to write the procedure what I am going to write now. Yes, here we have labeled the diagram. Please go through this and you should also mark. Then after that we have written the procedure according to my explanation. Yes, copy from here to here. After that I will go for writing Maxwell's right hand grip rule and also the factors on which the field strength depends. Observe. Here I have written the statement of right hand thumb rule. It states that imagine a man holding a straight conductor carrying current in his right hand. His thumb point indicates the direction of flow of current. See that. And encircled fingers indicate the direction of magnetic field lines. Here I am showing the direction. Anti-clockwise in this. And I have written both the cases. In case 1, the current is flowing upward direction. and the direction of lines of force anti-clockwise. Here current is flowing downward and the direction of lines of force, it will be in clockwise. But the pattern is same. If in the straight conductor, if the current is flowing, then the field lines pattern will be concentric circles that I have written. Yes. Please go for copying from there to here. Statement up to here, and these are the figures just for your reference. Yes. After copying this, you have to write this one. This is about factors on which field strength depend. Where the field strength is produced? Around a straight conductor in which current is flowing, right? And we have already explained that it depends on the amount of current. As current increases, field strength also increases. And another one is number of turnings, that is rectangular coil. As it increases, then field strength also increases. But another one is there. It is distance from the conductor. Observe, in this case only, this is the conductor and here these are the field lines. I go for naming them as A and B. Observe the distance of A from this conductor. Distance of B from this conductor. Which one has more field strength? A or B? It is A. Why? Because radius is same and it is very close to the conductor. Hence the field strength is more in case of A than B. And both are radii only, 1 and 2. As the distance from the conductor increases, the field strength will go on. What happened? Decreasing, right? As the distance decreases from the conductor, then field strength increases. That means as one quantity increases, other quantity decreases. As one quantity decreases, other quantity increases. Then whether it is directly or inversely? Yes, it is inversely. That is, I go for taking this distance as R. So it is B is inversely proportional to distance. Distance in bracket I can take it as R. Clear? Yeah, please do remember this. Just one simple example. Assume that this is the conductor. Now current is flowing from A to B. Then here lines of force are formed around this conductor at all the points. Around all the points, here also, here also. Then what is the pattern of lines of force in this straight conductor carrying current? Obviously you can say that concentric circles. Then could you tell what is the direction of lines of force? Anti-clockwise or clockwise? Yes, you are right. It is anti-clockwise because I said current is flowing from A to B. Then lines of force will be in the opposite, in the anti-clockwise direction. What about at point A? There also it is same because current is flowing from A to B. Now observe. I'll go for taking this as P, this as Q. I'm giving the radii. This is R1 and R2. At which point, that is P and Q, field strength is maximum. Where? Either P or Q. It is at P. Why? The reason is radii at P is smaller than that of radii at Q. As the distance decreases, field strength increases. As the distance increases, field strength decreases. Clear? Yes. Please go for copy these points. Dear students, now first one has been completed. Straight conductor carrying current. Now we are going to study the pattern of lines of force, that is magnetic field lines, around a circular conductor carrying current. See, this is the diagram. Very simple way of drawing it. See, just observe here. You go for drawing two concentric circles. Okay. Then after that, you just rub along the diameter like this. See that? After rubbing, go for taking scale and pencil and draw a rectangle. See that? This is the way. Clear? Is it not simple? And rub this part. Draw two parallel lines and draw here one more rectangle. It is a simple way of drawing. Look here. Procedure is very simple. First, we have taken a rectangular cardboard and make two pinholes near the opposite ends of a cardboard. Then take a long copper wire and should pass the copper wire through the first hole and then through the second hole, such that you have to make a complete loop, that is one circle. Like that, you may go for taking any number of turnings. See, first you pierce from here, then you pass that wire here, again you come back, then you come to next hole and first hole, second hole, like this. Then at last you will get the free ends, and these free ends should be connected to terminals of a battery along with the switch. Here also we have to follow the same procedure. So take number of iron filings and go for spreading them on the cardboard evenly. Clear? Okay. Next, what should be done? Close the circuit by pressing the plug key. Then what happens? Current flows from positive terminal to negative terminal. Just keep observing. From positive terminal, observe the direction of flow of current. Look here, then here. Just keep observing. Then it come inside. Then here. Then it goes there. Then finally it comes here. Clear? So the direction of current from positive terminal to negative terminal. Then after that, then go for tapping the cardboard once or twice. Dear students, we have already learned that as soon as the current flows through the conductor, magnetic field is developed. Now the field is developed here, this part, and this part here, and around this loop as well as here. Then as a result of it, iron filings, they are under the influence of magnetic field which is developed around the conductor. Hence they have a tendency to move towards the wire as it acts as a magnet. Clear? Then after tapping, iron filings will start arranging themselves around the conductor in this way. Just keep observing how the iron filings are arranging. You can notice that. And can you tell what is the pattern? Yes, it is concentric circles. Here also, circles having same center with different radii. What about at this end? In the same way. Here, iron filings will arrange themselves in the concentric circular pattern. Yes. And you can also notice that at the middle, how the lines will be arranged. Just keep observing. Now you tell what is the pattern of lines of force? Yes, there are two types of pattern in case of circular conductor carrying current. One is concentric circles near the conductor. See that? Here concentric circles, here concentric circles. But at the middle of the conductor, it is straight and parallel. Right? Got it? Pattern is concentric circles near the conductor and straight and parallel at the middle of the circular loop. Now we have to show the direction of lines of force. Look here, current is flowing here on the left hand side. Whether current is flowing in the upward direction or downward direction. It is upward direction. What is the pattern of lines of force? Just hold like this. Yes, thumb points. It is upward and encircle fingers. It is anti-clockwise. Here you can show the direction in this way. Clear? Similarly, when you come to on the right side, the direction of current is downward, right? Here upward and here downward. If the current is flowing downward, then the direction of field lines will be clockwise. This clockwise direction can be shown in this way. Understood? Yes. What about here? See that it comes here clockwise, here anti-clockwise. See that? It is straight and parallel. And do remember, if whatever the magnetic field is developed, wherever it is, if the field lines are straight and parallel, then we can say that the magnetic field has uniform magnetic field. There will be constant magnetic field at this point. It is uniform magnetic field. If the pattern is concentric circles, you go for drawing like this. Uniform magnetic field, see that? Straight and parallel. Even you may draw like this also. Lines should be straight and they should also be parallel to each other. Got it? Yes. Now I go for writing the procedure, and before that, one more important information. Like in case of straight conductor carrying current, whether the field strength depends on any factors in this case? Certainly. Here, let us come to know the factors on which field strength depends. Obviously, again, one is the strength of the battery. The strength of the battery, that indicates the amount of current. As the voltage of the battery increases, current also increases. As current increases, then more amount of field is developed. As more amount of field is developed, then strength, obviously it will be more. Hence we can say that magnetic field depends on the amount of current. As the current increases, field strength increases. Current decreases, field strength also decreases. Clear? Similarly, next one. Observe it. Observe this loop. Here, how many rounds are there? Once, then twice. You just measure the field strength when 2 rounds are there. Similarly, when 4 rounds, 10, 20, 15, 20, 25 and so on, as you go on increasing the number of turnings, field strength also increases. Why? Observe it. Here, some amount of field strength is developed around only one loop, and next the same amount of is developed around the second loop, next around the third loop, like this. Here the field strength will go on adding. Hence the magnetic field strength increases as the number of turnings increases. Clear? Here I'll write. Field strength is directly proportional to number of turnings. As number of turnings increases, field strength increases. As it decreases, field strength also decreases. Next, another important point. Look here, with respect to these concentric circles which represents the lines of force, as the distance of the lines of force increases, what happens to the field strength? Decreases. Because if the lines of force is very close, it will be having more strength. If it is far, its strength decreases. As one quantity increases, other quantity decreases. As one quantity decreases, other quantity increases. Hence we can say that field strength is inversely proportional to distance, nothing but radius of the what? It is field lines. Not only this, one more important factor is there. Observe this pattern. Observe this conductor. It is in circular shape. If this diameter of this circular loop decreases, what happens? As it decreases, the field strength, see, lines of force will come still closer to each other. What will be the strength of the magnet? Obviously, increases, right? As the diameter increases, field strength decreases. We can write the 4th point as field strength is inversely proportional to diameter of the loop or circular conductor. As the diameter increases, field strength decreases. As the diameter decreases, field strength increases. Followed? Dear students, you all may be thinking that if this circular conductor acts as a magnet because field strength is developed around it, then it must be having the poles, right? Then how to identify the poles? For that, we have a rule. Let me tell you that rule. That rule is clock face rule. It is clock face rule. And in this, you have to imagine here you are standing in front of the board, and this is the circular conductor carrying current. You just observe the direction of current, how the current is flowing. It starts from here. See that? From my left hand side. From my left, here first right, then circle, that is clockwise, then towards my right. Clear? So can I draw like this? In this way. Here, when you observe directly the circular conductor carrying current, in which direction the current is flowing? Yes, clockwise or anti-clockwise? Yes, it is clockwise. Clear? That phase acts as south pole. In case of circular conductor carrying current, if the current flowing in the circular conductor appears as clockwise direction, then that phase acts as a south pole. Very simple to understand. Observe it. You will write S and observe the direction. Here, direction. And here. Clear? Next, imagine that you are behind this board. Assume that the board is transparent and you are behind this board, but figure is there, and that means you will stand like this. Then how the direction of current appears for you when you stand here? Yes, when you stand here, it appears as if it is flowing in the anti-clockwise direction. Clear? Yes. Here also again the same pattern in this way, but the current, it looks like as if it is flowing in the anti-clockwise direction. Then that phase acts as north pole. See the direction. Understood? Yes. And here, whatever the phase of this circular conductor you are seeing at present, this is south. Back side, it is north. So that is clock face rule. According to this rule, you have to imagine that the current flowing in the circular conductor is in the clockwise direction. That phase acts as south. If the phase in which the current flowing appears as anti-clockwise direction, then that phase acts as north pole. Clear? Yes. Dear students, now I am going to write the procedure, then the factors on which it depends, then clockwise. First, you go for drawing this figure and try to level yourself. Hope that you have drawn, and even I had asked you to level the parts. You just check that. This is the conductor, nothing but wire, and this is direction of flow of current. Whereas these arrow marks indicate the direction of lines of force, and also these are lines of force. Next, and this is cardboard, and it is wire. This is battery and this plug key. Even you can go for naming this. What is this? It is uniform magnetic field. Clear? And then here I have written the procedure. You should copy the same. That is very simple. Take a rectangular cardboard and make 2 pin holes near the opposite ends of the board. Then next point, take a long copper wire, pass the wire through the holes such that it should make a loop, more than one loop. Next, Another point, connect the free ends of the wire to the terminals of a battery along with the switch. Clear? Fourth point, spread the iron filings evenly on the cardboard. Then fifth point, close the circuit, then tap the card. Next, another point, it is observed that iron filings start arranging themselves in concentric circles near the conductor, straight and parallel at the middle of the circular loop. Next, so and the pattern is concentric circles as well as uniform magnetic field. Here I have written the definition of uniform magnetic field. If the magnetic field lines are straight and parallel, then the magnetic field is said to be uniform magnetic field, and here I have drawn its figure as well. We also know that what all the factors on which the field strength depends. It may be the amount of current and how it is I have written here. Number of turnings of the loop. Next, distance of each line of force from the conductor. Not only that, even the diameter of this circular conductor or loop. Got it? Next, another point is that it is about clock phase rule. Please go for copying from here to there. Yes. Dear students, here I have written clock phase rule to identify the pole of a circular conductor carrying current as it acts as a magnet. Here we have written that. Please go through this. It states that if the current around any face of the circular conductor carrying current appears to be clockwise direction, then it acts as, that phase acts as south pole. And if the current flows appears to be anti-clockwise direction, then that phase acts as north pole. So with respect to that, here I have drawn the figure as well. So you have to copy this. I think you have copied up to here. Now you are going to copy from here to here. Okay. Dear students, before going to conclude the class, let me give you an information. Whatever we have covered with respect to this chapter today, please work out today itself. Don't keep anything pending. And another one is, we are going to study the pattern of lines of force around a solenoid carrying current. So that will be discussed in tomorrow's class. And one more information is, you all know that yesterday we conducted the weekly test, maths weekly test 8. So now let me show you the question papers. Please go through this question paper and you can take the screenshot and use it for practicing. See that it was conducted for 25 marks, and even the questions are written according to the section wise. 1 mark questions in section A, 2 marks questions in section B, and 3 marks questions are included in section C. Observe it. This is first page and the second page. These are the questions. Now, next, third page. This is total 13 questions are there. Please use them for practicing. Okay. Now, so let me conclude the class. So with this, let us stop the class. Thank you very much.